today we're going to get into Chapter 11, Section 3. Chapter 11, Section 3, all about what's called limiting reactants. And we're going to use a lot of the skills, the techniques that we have been building over the last two chapters. Well, over chapter 10 and then the first two sections of chapter 11. We're going to be using a lot of those skills. Honestly, today, we're not really introducing any new skills or techniques. So this is all going to be stuff that you've seen before. We are just going to apply it to real-world situations. Now, whenever I teach this, I have some students that it just confuses for some reason. Not sure why. Some people just, it doesn't make sense to them. So, to try and help, I have come up with this, I guess, example that is a lot easier to understand sort of the concept. And what we're going to be dealing with are cheese sandwiches. Okay? A cheese sandwich. Now, as we go through this, okay, when we talk about the examples of the cheese sandwiches, you're probably going to think this is super simple. Obviously, you know, why are we taking time to do this? But you'll see as we go through. So, let's assume that you have some friends coming over and you're going to, well, I'd say have a party, but obviously you're probably going to be studying chemistry because chemistry is awesome. So, anyway, at some point, you all decide that you're hungry. So you're going to need something to eat. And you decide you want some cheese sandwiches. Okay. All right. Now we're going to make, just to make this simple, we're going to make these pretty basic cheese sandwiches. So if you take 2 pieces of bread and add 1 piece cheese, that gives you 1 cheese sandwich. Does everyone agree? Take a piece of cheese, put it between 2 pieces of bread, you got a cheese sandwich. Okay. So let's say you go to the kitchen, go to the refrigerator, you pull out your pack of cheese, you have 10 slices. Then you go and you get the bread. And you find that you have 12 pieces of bread. How many cheese sandwiches can you make? 6. If you have 10 pieces of cheese, why can you only make 6 sandwiches? Because you've run out of bread. Okay? what you did without even thinking of it, said, which one are we going to run out of first? Okay. And you came up with bread. Makes sense. Okay. And that was really, really simple, right? That's what we're going to be doing today. But for some reason, once we go from sandwiches, chemistry, people say, I don't know how to do that. Okay. But all we're doing, we're finding the limiting reactant. What that means, we want to know when you mix these things together, which one is going to run out first, because that limits how much you can make. We ran out of bread, and that limited the number of sandwiches. We had extra cheese. How many extra pieces of cheese do we have? 4. Once again, you can do it without even really thinking. Is that okay? We could have made 10 pieces, or we could have made 10 sandwiches with the cheese, but we ran out of bread after 6, so that means there's 4 pieces left. Okay? Pretty darn straightforward. Let's set up a unit multiplier just so that you can see that this is how it's going to work. Okay? What we've done is used a mole ratio. So we said we have 10 cheese. Our mole ratio says that for every 1 cheese, we can make 1 sandwich. Okay. So that means we can do 10. And then we do the same thing down here and compare. 12 bread. For every 2 bread, we can make 1 sandwich. So this time we get 12 times 1 divided by 2, 6. Okay. See? That's what you're doing in your head. And it makes a lot of sense when we're dealing with sandwiches. Okay? Because it's something real and tangible that makes sense. We're going to do the same thing, but with chemistry now. Okay? So hopefully you won't think it's too overwhelming when we switch to chemistry. Now, let's look at example problem 5 on page 382. Like I said, none of this is brand new. All of the things that we're doing today are calculations that we've done in the past. We're just applying them in a new way. So the question reads, the reaction between solid white phosphorus, which is P4, and oxygen produces solid tetraphosphorus decoxide, okay, P4O10. This compound is often called diphosphorus pentoxide because the empirical formula is P2O5. Okay? But the actual formula is P4O10. That's what we want to do. So we have 2 parts here. Determine the mass of P4O10, which is formed if 25 grams of P4 and 50 grams of oxygen are combined. Okay. Second part, how much of the excess reactant remains after the reaction stops? So, we in last class, we said there was one thing that you always needed to make sure you were starting with as a stoichiometry problem. What was that? A balanced equation. We have to have the balanced equation. Okay? So we've got P4 and oxygen giving us P4O10. So, not balanced, but this one's actually really easy to balance. Phosphorus, we have 4 on both sides already. We need 10 oxygen, so we just put a 5 right here. Okay, now we're balanced. So we've got our equation. Now, the interesting thing is, you might look at this and say, well, we only have 25 grams of phosphorus, so that's obviously going to be the limiting reactant because we have 50 grams of oxygen. But it doesn't always work that way. You actually do have to do the work. Okay? Now, once again, the book goes through the steps just a little bit differently. It breaks them out into different steps. So either way, it works. You're going to get the same answer. Okay. But what we can do is we say we've got 25 grams phosphorus, 50 grams of the oxygen. Okay. Just like we did with the cheese and the bread, we want to see which one is going to run out first. And to do that, we need to compare the potential amount of product you can get. So we're going to say if all 25 grams of the phosphorus gets used up in this reaction, how much of the P4O10 are we going to get? And all that is a stoichiometry problem. Okay? So we're going to start with what we know. All right. Now we have grams. What do we need to do if we have grams? We need to change to moles. Okay. So we go to the periodic table. We find phosphorus, number 15 right there. 31. So about 31. Okay. It's 30.97 something. But anyway, we take that and we multiply it by 4. And what we end up getting, we'll use the value here in the book, is 123.9 grams. So that's our conversion factor. We're going to put the grams on the bottom because we're trying to get rid of grams. Okay. So the next thing that is going to happen is our mole ratio. Our mole ratio. And this one we get from the balanced equation. That's why we need the balanced equation. Okay. We're trying to get rid of the white phosphorus. So there's a 1 implied there. So we say 1 mole of the white phosphorus. It reacts, gives us 1 mole of the P4O10. Okay. At this point, if all we are looking for is the limiting reactant, we can stop. We can compare moles of the P4O10. Okay? But since the problem asks for how much is going to be left over, we may want to have that in grams. Okay? So it's not a bad step to just put this back into grams. And for the P4O10, the 4 phosphorus, 10 oxygen, we add all that up. And what we actually get is 283.9. Okay. So now, we grab our calculators. Okay, 25 times 1 times 1 times 283.9, 1,097.5, all over 123.9 times 1 times 1. And that gives us 57.3. 57.3 grams P4O10. Okay. We're halfway there. Because now we have to do the same thing, but for the oxygen. Okay. Remember, that's what we did with the sandwiches. He said, how many sandwiches can we make with cheese? How many sandwiches can we make with the bread? Which one is lower? We're doing the same thing here. Okay. Obviously, you didn't need a calculator to do the calculations of the cheese and the bread, but it's the same basic principle. Okay. So we're going to start with our oxygen. We're going to convert it. We go to the periodic table. We'll round it off to 32. Okay. We now need a mole ratio. This one's a little bit different. Because we now have 5 moles of oxygen, producing 1 mole of the P4O10. But luckily, this last step is exactly the same. So if we double check, so grams has been gotten rid of, moles, oxygen, moles. Now we're just left with grams of the P4O10. Again, we can go to our calculator. Okay, 182 grams of the P4O10. So, what's our limiting reactant? Which one do we get less of? Which one of these two numbers is smaller? Okay. That means that is our limiting reactant. Okay. That is our limiting reactant. So we know P4 is going to be a limiting reactant. Okay. And it says determine the mass formed. Well, since we did this last step, we already have that. So it's 57.3 grams. Okay. So that is the first half of this question. Okay. Which one is limiting reactant? The white phosphorus. How much P4O10 is going to be created? 57.3 grams. Okay. The second part, how much of the excess reactant remains after the reaction stops? Okay. This is just another stoichiometry problem. And when we do this, we start with the excess reactant. Start with the excess. Once again, we have to change it to moles. The nice thing about the excess is that you've gotten a lot of the calculations already done. Okay. So we already have that one. Grams cancels out. Now we need our mole ratio. The mole ratio comes next. In this situation, we're getting rid of oxygen. Okay, so 5 moles of oxygen. Instead of using this, we want to know when all 5 moles when all of the P4 is used up, how much is left here. So these are the two things that we're taking with the ratio. Remember, you can use any two things. You can use any two things in that problem for your mole ratio, where whatever you need. Okay. So put our 1 mole P4. I'm doing this wrong. You want to start with your P4. Looking at it thinking, how am I supposed to get to what I want? So, but it's the same thing, so start with 25 grams of the P4. We have our 123.9 grams there. Now we put 1 mole P4, 5 moles of oxygen. Because what we want to know, since this is the limiting, the reason why we're starting with the limiting is because when that is all used up, this calculation is going to tell us how much oxygen was used. How much oxygen was used. So, and then we go from this to grams. So 32 grams to 1. So grams is canceled out. Mole, 4, mole. So now we have, when we do this, we have grams of oxygen that is actually used. Okay. So go back to the calculator. 25 times 1 times 5 times 32 is 4,000. 123 times 1 times 1. So we're using 32.3 grams. Now, is that the amount that we have left over? No, it's what we actually used. So how do we find the amount that was left over? We take what we started with, the 50, we subtract that. Very good. Which, so 50 minus 32.3 gives us 17.7. So that is, we have 17.7 grams. Okay. Let's do another example. Same thing. Let's do another example, make sure that we've got it. Okay. Let's look at one of these practice problems here. Let's just do number 23. So the reaction between solid sodium and iron oxide is one in a series of reactions that inflates an automobile airbag. Okay. So it gives us the balanced equation. And we always like it when it gives us the balanced equation because that saves us a little bit of time having it balanced. So and it tells us we have 100 grams of each. Okay. And we need to determine basically all of the other things that we did for the previous thing. Okay. Which one is limiting? Which one is the excess, which is basically whatever one is not limiting? How much solid iron is produced? And how much of the excess reactant is still there? Okay. So once again, we're going to take each one of these and see which one runs out first by calculating how much we can make with 100 grams of both of them. So we start with 100 grams of sodium. And we look at our periodic table, and we see sodium, we'll say 22.99. So I'm not writing out all of the conversion factors. If it still helps you to write them out, great, go for it. But I'm just to sort of save time and writing and everything, I'm just going to start putting them in there. You guys are probably, if you're not to that point, you're probably close to being able to do that on your own. So, then we do our mole ratio. Sodium is what we're trying to get rid of. So 6 moles sodium. Now it's interesting because I could say 6 moles of sodium produces 3 moles of the sodium oxide. And that would get us our limiting reactant, no problem. But since the problem itself asks for the mass of iron, we're going to pick that one. Okay. And if we're just looking for the limiting reactant, we can stop there. Tell you what, we'll stop there for this one, and so you can see how that works. So we pull out a calculator. As we can see, grams, sodium, and moles are gone. Okay, so 100 times 1 times 2, that one's easy.
Wendy and Nathan Dolly, please come down to the office to check out. Wendy and Nathan Dolly, please come down to the office to check out.
And then 22.99 times 6, 137.94. So what we're left with is 1.6450 moles of iron. But if we do the same thing with our iron oxide, okay, go to the periodic table. We know we're going to change it to grams. So we look at iron, 55.845, but there's 2 of them. And oxygen, 15.999, but there's 3 of them. That gives us 159.687 grams. Now we put in our mole ratio. This one has a 1. So 1 mole of the Fe2O3 gives us 2 moles of iron. We're going to stop there because we're just going to figure out how many moles of iron, because we can compare that just as well. So once again, the top is pretty easy. 100. And then this one, the multiplication is easy again. Once you get to this point, you may be able to see which one is going to be our limiting reactant. If you are just do math in your head or whatever. But just put it in your calculator anyway, just because you can. And what we end up with is 1.252 moles of iron. Okay. So we look at this. The iron oxide is going to be used up first. The iron oxide is going to be used up first because we can only produce 1.252 moles of iron with 100 grams. Okay. So the iron oxide is limiting, which means sodium is excess. Okay. And then, since it wants grams, okay, you can take this right here and convert it to grams. All you have to do is go to our periodic table once again. Iron, 55.845. Grams, 1 mole. Okay. And what we end up with is 69.92 grams of iron. Okay, so now we've figured out limiting, excess, mass of iron that you can have. But there's one more thing, the mass of the excess reactant that remains. So to figure that out, remember we're going to start with the limiting. Don't make the mistake that I did first and start with the excess. Okay, start with your limiting. And change it to moles. Luckily, we already know the number. Okay. Now we're going to do our mole ratio. So we do have one of this. But this time, we're trying to see how much sodium is used up. So we go 6 moles sodium. And since it asks for a specific mass, we're going to throw on one more conversion factor to go from moles of sodium to grams. Okay, but we already have 22.99 grams in 1 mole. So do some unit canceling out. So we got grams, it's gone. P2O3 is gone. Moles, 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 moles. We're left with grams of sodium, which is exactly what we want. Now we're ready to go back to the calculator. So 100 times 1 times 6 times 22.9. 13,740. 159.687 times 1 times 1. That's easy math. Okay. That tells us we've used up 86.04 grams. But that's not quite the answer. That's how much we used. We want to know how much is left. So we subtract it from our starting. And we get 13.96 grams of sodium. That's our unit left. Grams of sodium left over. Yes.
The word excess means right out.
Excess is the extra. It's so the limiting is what you run out of first. Excess is what you still have left. So yeah, anytime it asks for how much excess, how much of whatever it was that didn't get used up is left. So like I said, honestly, there was no new concepts that we introduced today. Okay? This is all stuff that we worked on and did, skills that we built last chapter and first part of this chapter. Okay? All we've done is said, well, let's apply it to figure something out. Okay? So if you were comfortable with the homework from last time, this should make sense. Okay, we're just using it. Yes.
So I just don't understand why is it like the 2 mole, why is it FE at the top?
Yeah, this one. Because we're getting this number from our balanced equation. Right there. Okay, so this mole ratio, you take whatever your coefficients are. So 6 moles of sodium, if all of that reacts, we're producing 2 moles of iron. Okay, that's where this mole ratio comes from. It's like this one. So one mole of the iron oxide produces 2 moles of the iron. Okay? 1 mole of the iron oxide reacts with 6 moles of the sodium. So this step That's why we need a balanced equation. Okay, so whatever compound or element that you're changing from and to, just pull those coefficients straight from the equation.
Okay.
All right. Any other questions before I let you start on some homework?
Maybe it's weird. Or my body is just not producing enough heat. I don't know what it is. Or I just find some more muscle. That's probably what I need to do.
Anyway, homework for today. I'll stick it right in here. Only 6 problems because most of the problems you're going to have to do a couple things like this. Not super intense, just a little bit time consuming.
Amazing.
Yes.